Hello, AP Chemistry students. These are your notes on 8.7, the pH and the pKa. So our enduring understanding is that a buffered solution resists changes to its pH when small amounts of acid or base are added. In this lesson, we will learn to explain the relationship between weak acids and bases in solution at a given pH and the pKa of the conjugate acid or the pKb of the conjugate base. So recall the general equation. Ha plus water yields hydronium ion plus the conjugate base. So the equilibrium constant, or acid dissociation constant, is equal to the concentration of the hydrogen ion times the conjugate concentration of the conjugate base divided by the concentration of the acid. So to see the relationship between pH and pKa, we need to take the negative log of both sides. So we'll take the negative log of the Ka, which gives us pKa. And then we'll take the negative log of this expression. So the negative log of this expression, I can separate out the concentration of the hydrogen ion. Negative log of this will give us the pH. And then I'm left with this concentration of the conjugate base divided by the conjugate concentration of the acid. So by rearranging this equation, adding the negative log to both sides, I get pH is equal to pKa plus the log of the conjugate acid divided by the concentration of the base. This is that Henderson-Hasselbalch equation that we saw before, and it tells us about our reaction profile for an acid. Let's remember that the midpoint has special significance. So the midpoint was identified by finding the volume, or number of moles, at the equivalence point. So we'll call this V because it's volume on this graph. And then the midpoint occurs at 1/2 of V. And so at this point, the pH is equal to the pKa. Now here's the reason for this. So the pH is equal to the pKa because the concentration of the acid, or Ha, is equal to the concentration of the conjugate base, or A negative. So the log of the base, conjugate base, divided by the acid concentration is going to be 0 because when they're equal, this conjugate acid divided by our conjugate base divided by the acid is equal to 1, and the log of 1 is 0. So we can use this to infer things about the concentrations of the acids and bases. When the pH is less than the pKa, that tells us that the log of the base divided by the acid has to be negative. And so if that term is negative, then the concentration of the acid is greater than the concentration of the base. If the pH and pKa are equal, then we must be at the midpoint. So the concentration of the acid and base are equal. So we have the log of 1. That comes out to 0 because concentration of acid and base are equal. Then, if pH is greater than pKa, well, that tells us that the log of the concentration of the base divided by the concentration of the acid has to be positive. So our concentration of our acid is greater than less than the concentration of the base. So some things to keep in mind. If we're taking the log of a number that is less than 1, then that log will be negative. If we're taking the log of 1, that value will be 0. And if we're taking the log of a number that is greater than 1, then the value of the log will be positive. Considering Le Chatelier's principle, we recall that the lower the pH, that means we have more of these hydronium ions. And hydronium ions were a product in this equation. So when we have more of a product in an equilibrium reaction, the reaction will shift to the left, producing more HA, acid particles. When we have a higher pH, that means we have less of the hydronium ions. And so having less of a product means the reaction will shift to the right, and we'll get an increase in the conjugate base. So by knowing the pKa, we can predict the ratio between the concentrations of the acids and bases at any pH. We can also infer some things based on the value of the log of the base divided by the acid. So when this term is equal to 1, that means that the ratio between the base and the acid concentrations is 10 to the first power, which tells us that we have 10 times more base than the acid, or about 91-ish% base and about 9% acid in the mixture. Likewise, when this value is 2, that means that the ratio is 10 to the second power. So we have nearly 100 times more base than acid. Similarly, when we have -1 for this term, that means that we have a ratio of 10 to the -1 power. So there's more acid than base. And in fact, it's 10 times more. So we have about 9% base and about 91% acid in the mixture. And then when this term is -2, we'll have a ratio of 10 to the -2, which means that we have 100 times less base than acid. So about 1% base and about 99% acid in the mixture. A lot of times when we do acid-base reactions, we use something called an indicator. It's a way to see if a reaction has reached its equivalence point, and it changes color at the pH of that equivalence point. So we call the pH where the color changes the end point of the titration. Indicators are mixtures containing a conjugate pair of molecules, or molecules whose structure differ by a hydrogen ion. So one molecule is a weak acid, HA, while the other molecule is the conjugate base, normally A negative. So here's an example. This is methyl red. So IN here is for indicator, not the element indium. So I have A negative or IN negative, and we can see that the difference between these structures is right here at this nitrogen. So on our HIN, I have a hydrogen here. But on our IN negative, there's no hydrogen there. Instead, we have a double bond to the other nitrogen. So we call this protonated when there is a hydrogen attached here. And we call it deprotonated when that hydrogen is missing. So even though the chemistry of this methyl red is slightly more complicated than the simple removal of a proton, we can simplify this for our own purposes and say that, treat it as if it were a weak acid and base conjugate pair. So then it will follow the reaction. HIN plus H2O yields hydronium ions and the conjugate base of the indicator. And we can use the Henderson-Hasselbalch, so pH is equal to pK of the indicator plus the log of the concentration of the conjugate base divided by the concentration of the acid. So this is helpful because we can choose a correct indicator for a particular reaction by finding the indicator that has a color change at the equivalence point of our acid-base neutralization. So we can use it to tell us if we have reached our endpoint. When we use a strong acid and a strong base, our equivalence point has a pH of 7. So it's important to choose an indicator that has an endpoint near 7. When we have a weak acid and a strong base, the equivalence point is going to be greater than 7 because the conjugate base of the weak acid is in the solution. And so we should choose an indicator that has an endpoint above 7. When we have a weak base and a strong acid, the equivalence point is going to be less than 7 because the conjugate acid of the weak base is in the solution. And so we should choose an indicator that has an endpoint below 7. So here's what I mean by that. So each of these indicators has a range for its color change. So for example, this methyl violet, its range is almost 0 to about 1.4, I would say. And so if I'm looking to titrate to an endpoint in this range, I would choose this because it's going to show me that my acid-base reaction has taken place. So if I have, for example, a strong base and a weak acid, I'm going to choose this thionyl blue because its range is near an equivalence point of 9. Okay, so your equivalence point, or your pKa for the weak acids and bases, should fall into the range of the indicator for it to be a good indicator for that titration. Also, it's not strictly true to say that an indicator like methyl red, for example, is red in acid and yellow in base. So here, 7 is neutral, okay? And so methyl red is this one right here, and the entire range of this indicator falls in the acidic half of the pH scale. So it would be safer on a free response question to say that methyl red is red at low pHs and yellow at higher pHs. So in a mixture, if one color is 10 times stronger than the other color, our eyes will only detect the dominant color. So our ranges, if we look back to the previous page, our ranges tend to be just about 2 pH numbers across, right? Just about. This one, about there. So the reason for that is based on where the endpoint of the titration is. It'll be in the middle of this range where it starts to change color. So we'll see yellow, for example, with methyl red, when the pH is equal to the pK plus 1. And we'll see red when the pH is equal to the pK minus 1. So again, about 2 is the size of the range of most indicators. So again, we can see the ranges here are about 2 pH units. Okay, so here's the I-do. Alizarin red, X, is an acid-base indicator that changes from red at a pH of 4 to yellow at a pH of about 5.5. Remember that indicators are chemicals that have different colors when protonated and deprotonated. So, would the protonated or the deprotonated form of alizarin red be red? Well, protonated, recall that a pH of 4, the lower the pH, the more free hydrogens there are. And when our pH is 5.5, that means we have fewer free hydrogen ions. So when we're at the red color, we have a pH of 4. So that means there are more free hydrogens available to react with our indicator. So that means we'll have more of the protonated forms of alizarin red. Part B asks whether this indicator would be most effective for a titration with sodium hydroxide of acetic acid, which has a pKa of 4.75, or the titration of hydrochloric acid, HCl. Well, NaOH is a strong base. If I have a strong base and a weak acid, I'm going to end up with, I'm going to leave this one for a second. Let's talk about HCl. So NaOH and HCl. These are a strong acid and strong base. Since I have strong acid and strong base, the end point of that titration is going to be at 7, a pH of 7. The pH range for alizarin red is 4 to 5.5. So 7 falls outside of that range. It's not going to be useful for that titration. Since acetic acid has a pKa of 4.75, that would be in the range of alizarin red. So it would be more useful in a titration with acetic acid and sodium hydroxide. Okay, let's look at our redo. The pKa of nitrous acid is HNO2. I'm sorry, the pKa of nitrous acid, HNO2, is 3.16. A buffer solution is made by mixing the acid and sodium nitrate, NaNO2. When bromophenol blue is added to the mixture, a blue color can be observed. Which species is present in a greater amount, protonated HNO2 or deprotonated HNO2, or deprotonated NO2 minus? So, bromophenol blue, if we look at the scale that's on our packet, the range for bromophenol blue is 6 to 7.7. And on the end that is 6, this is yellow. And on the 7.7 end, well, this is blue. So the blue end is going to be our more basic end, which means that we have more of the conjugate base or the deprotonated NO2 minus.